So for section 14.4, we're going to talk about tangent planes. Our learning goals for this section are numerous. Some of them are going to be review from 261 and others are going to be new, but I'm going to hold you accountable for both sets of information. And I'm going to try to be clear about what I want from each set. So the review items that I want to emphasize are the ideas of dot product, cross product, and equations for planes. And the notation is going to be slightly different than what you saw in 261. The new content that we're going to talk about is being able to find the linearization of a two-variable function and describe that linearization graphically and algebraically, to find equations of tangent planes, and finally to use linear approximations to estimate functional values. So to start off with, let's look at some definitions. The dot product of two vectors, I'm labeling my vector 1 as the vector A, B, C. You could think of this as having an x-coordinate of A, a y-coordinate B, and a z-coordinate C. My other vector L, M, N. When I take the dot product of these two vectors, by definition, it's the first components multiplied together, in this case AL, plus the second components multiplied together, which in this case is BM, plus the third components multiplied together, which is Cn. Notice that this output is going to be a scalar. It's going to be a single real value. It's not a vector. Not a vector. So I dot product two vectors together as an input, and I get something out that's just a number and not a vector. One of the properties of dot products that I'm going quickly because this is review. The dot product of two vectors is one way to tell the angle between those two vectors. And by definition, the dot product is the magnitude of the first vector times the magnitude of the second vector times the cosine of theta, where theta is the angle between the two vectors. One of the consequences of this is that if the two vectors are orthogonal to one another, then the angle between them is going to be a 90-degree angle, and the cosine of 90 degrees is 0. So that means if the dot product of two non-zero vectors is 0, then they are orthogonal. Next, we're going to look at the definition of cross product. The cross product of two vectors, v1 and v2, is going to be the determinant of this 3x3 matrix. And this is something that you may not have seen previously. So when I take the cross product, I'm looking at I, j, k, where I, j, and k are each of my component vectors, where I is given by the vector, maybe I should write this here, I is given by the vector 1, 0, 0, j is given by the vector 0, 1, 0, and k is given by the vector, vector 0, 0, 1. So the cross product is going to be the determinant of this 3x3 matrix. And recall determinants for 3x3 matrices, it's going to be I times B times n minus C times n. Another way to write this is I times the determinant of the matrix given by the things that aren't in the I column. Then I subtract the determinant of the things that are not in the J column. And if I write it in this order, it's subtraction. And finally, I add K times the determinant of the remaining things. And recall, to find the determinant of a 2x2 matrix, it's going to be Bn minus Cm times I minus the determinant of this matrix is An minus Cl times the vector j, and the determinant of the final matrix is given by Am minus Bl times k, which results in a vector. You can write this. The ith component of the vector is the first is the x-coordinate of the vector, the jth component is the y-component of the vector, and the kth component is the z-component of the vector. Finally, I want to record some of the geometry consequences. We recall for cross products, if I take the cross product of two vectors, the resulting vector is going to be a new vector, and that new vector is orthogonal to the first two. Orthogonal meaning if I have two vectors, they're going to define a plane, and the third vector is going to point outwards. Oh, this is really bad, maybe on this camera. Orthogonal to the previous two, even if the previous two weren't orthogonal to each other. And one final piece of geometry, the magnitude of the cross product is equal to the magnitude of each of the individual vectors times the absolute value of the sine of the angle between them. And that connects back with what we saw earlier with dot product, where it was the cosine of the angle between them. So now we're going to look at an example. Suppose I have two different vectors, v1 given by 1, negative 2, 4, and v2 given by 3, 0, 2. First, I'm going to look at the dot product of v1 dotted with v2. By definition, it's the first components multiplied together, which is 1 times 3, plus negative 2 times 0, the second components, plus 4 times 2, the third components. And what does that equal? That's 3 plus 0 plus 8, which is equal to 11. It's a relatively straightforward computation. Next, let's look at the cross product of v1 crossed with v2. Recall that that's going to be the determinant of the 3 by 3 matrix where i's, j's, and k's are along the top of the matrix. My vector v1 is along the next row, and it's given by 1, negative 2, 4. And my vector v2 is along the bottom row, given by 3, 0, 2. So when I look at the determinant of this matrix, I know I have my coefficient I times the determinant of the smaller 2 by 2 matrix, which in this case is negative 2 times 2, which is negative 4, minus 4 times 0, which is 0, minus j times 1 times 2. I'm looking at the determinant of the matrix that's not in this column. So 1 times 2 is 2, and 4 times 3 is 12, so it's 2 minus 12. And then my kth component, I ignore the things in k's column, and I have the determinant of 1 times 0, which is 0, minus negative 2 times 3, which is negative 6, so minus negative 6 becomes plus 6. And I can simplify all this. I find out that my vector is negative 4i minus 2 minus 12 is negative 10, so that becomes a positive 10, j. And 0 plus 6 is just 6, so I get plus 6, k. Another way to write this is the vector negative 4, 10, 6. This new vector is going to be orthogonal to both v1 and v2. And another thing to point out, why is this j negative? If I wanted to, I could take the determinant of the matrix 4, 2, 1, 3, and then this would be positive, and it just goes in a different order. But hopefully you are masters of cross products, and that's something that we can talk about individually as well. Finally, I want to talk about one way to describe the equation of a plane. It's in point normal form. You don't need to remember that name, but I like it because it gives a geometric intuition about why the plane equation is what it is. Suppose I have a plane through the point P naught given by x naught, y naught, z naught, and it has a non-zero normal vector n given by a, b, c. So what's that saying geometrically? Geometrically, that's saying that somewhere in three-dimensional space, I'm going to pick a point on my plane. I'm going to label that point P naught. And here's my plane. Shoom, 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 shoom. It's some tilty thing. And instead of defining it by sort of the slope of the plane, we're instead defining it by what's exactly perpendicular to that plane. And I'm labeling that perpendicular vector n, because every other vector that lies flat on this plane is going to be exactly perpendicular to this normal vector in every single direction. And how do we define that? We define it by saying, I know what it means to be perpendicular in 3 space. It means that the dot product is going to be equal to 0. So in order to be a vector that works on this plane, it better be the case that when I take that vector and root it at the point P0, it better be perpendicular to my normal vector. And that means that the dot product is 0. So that's my definition here. My point normal form for the equation of a plane is my normal vector dotted with my any old vector xyz that's been shifted to be rooted at the point P0 by subtracting each of the x0, y0, and z0 from the respective component functions. If I wanted to multiply this out, I could use the definition of dot product to say that my normal vector is given by ABC, and I can dot it with x minus x0, y minus y0, z minus z0, and have that all be equal to 0. It ends up being the case that that means that just by the distributive property, I am taking the product of A times x minus x0 plus b times y minus y0 plus c times z minus z0 has to be equal to 0. And my final piece, I can't quite fit it on this page, is going to be a times x minus, I can distribute the a times x0. This is just a scalar and this is just a scalar, and then move it over to the other side. And by distributive property, I get ax plus by plus cz is going to be equal to, adding to the other side, ax0 plus by0 plus cz0. This might be another form that you're used to seeing. But instead of memorizing this form, I like to think of it intuitively, knowing that my normal vector has to be perpendicular to whatever vectors that I want on the plane rooted at my point.